Good morning everyone. My name is Shubham Rai and I'm working under Professor B.P. Patel in the Department of Applied Mechanics. I'm going to give a presentation for PMRF Progress Review and my topic is Continuum Damage Mechanics of Laminated Composite Panels. So let's start. So this will be the flow of my presentation. Now, what is damage? So damage is evolution of micro cracks and voids which leads to stiffness or strength degradation of the material at macroscopic scale. For instance, where here we are able to see that at point P there is evolution of micro cracks and voids, which at the atomic scale is the reduction in number of atomic bonds. So this reduction in number of atomic bonds leads to stiffness degradation at the macroscopic scale. Now in figure 2 also we are able to see that this material, when we are loading and reloading this material, so this is undergoing two phenomena. One is its modulus is getting reduced, and second is there is permanent strain in this material. So this permanent strain is due to plasticity and this reduction in modulus is due to damage. So we are only going to model this reduction in modulus. That's why we have considered a brittle material for damage modeling. So the plasticity effect in that brittle material will be negligible. These are the other experimental evidences. So mainly we have taken this AS435016 carbon epoxy material. So it is a brittle material. Still there is nonlinearity present in this testing curves here and here. So it depicts that this nonlinearity is due to damage because this is a brittle material, so plasticity will not be present. These are the motivations behind damage modeling of various materials. So various materials undergo stiffness degradation upon loading and unloading. So here this is the example of electricity generation through wood through piezoelectric effect. The wood also is undergoing stiffness degradation, which is increasing its elastic compressibility and therefore increasing its output for piezoelectric effect. Now this wind turbine blades, bones and axons present in human brain, and then these composite panels present in PSLVs or missiles or other spacecraft structures, these all undergo stiffness degradation. So accurate mathematical modeling of the stiffness degradation using continuum damage mechanics will lead to precise design of this wind turbine blades, bone implants, precise treatment of traumatic brain injuries, and precise design of this composite panels used in PSLVs, missiles, and aircraft and spacecraft structures. Now we are going to model this damage mechanics through continuum damage mechanics. So here in figure 10 we are able to see this is continuum mechanics where there is no micro crack or void present. Continuum damage mechanics is applicable for this reason where there is evolution of micro cracks and voids. Now when micro cracks college to form a macro crack, thereafter we will use fracture mechanics. But in brittle materials, when the macro crack will be formed, so macro crack will be formed quasi-statically and it will propagate dynamically. So there will be less time, very less time that will be left for the crack propagation. So that's why it is very important to capture this evolution of micro cracks and voids. It will lead to accurate modeling or accurate design of the structures at the macroscopic scale. So how we can model that using continuum damage mechanics? So we assume that damage is continuously distributed over a finite volume of the element. So this is something representative. This is a representative volume element having a normal n. So on its plane there is some damaged area and there is some undamaged area. So damaged area is represented by delta SD and total area is delta S. So damage variable is essentially the ratio of damaged area to the total area. So if damaged area, if the area of RBE is completely damaged, so damage variable will be equal to 1, and if it is undamaged, damage variable will be 0. So damage variable will range from 0 to 1. 0 corresponding to undamaged state, 1 corresponding to damaged state. And this is one more variable that we are going to use. So it is effective stress, which is force over the undamaged area. So here on this plane there is damaged area as well and undamaged area as well. So effective stress is the stress that is acting on the undamaged area. So this stress will drive the damage. Now so there are some variables that we are going to use for continuum damage modeling. So first one is damage tensor. So it has 6 components in its principal direction. In Voigt's notation, it is represented by a vector. We are going to use two more damage variables. One is this thermodynamic damage driving force and this damage hardening function. So this thermodynamic damage driving force is thermodynamically conjugate to this damage variable, whereas this damage hardening function is thermodynamically conjugate to this damage parameter beta. So what is damage parameter beta? So here we are able to see, suppose this is black one is the stress strain curve for any material. So at this point P, when we will unload the material, so this green region represents the energy recovered, the elastic energy recovered, and the yellow region represents the energy dissipated. So this beta is accounting for this dissipated energy, and this damage variable is accounting for this elastic energy that is present in the body. How we can model the damage mathematically? So this is an overall overview of numerical solution procedure of continuum damage mechanics. So we'll start with the assumption of some damage variable, and then we will calculate compliance matrix and elastic constitutive matrix of damaged material, and then we will calculate tension stiffness matrix and stiffness matrix and force vector that is being applied on the structure, and then we will calculate incremental nodal degree of freedom vector through which we will calculate incremental strain. So we'll get the strain at the current iteration. Using that strain and the damage variable at the previous iteration, we will calculate the incremental damage variable using damage evolution equations. So the incremental damage variable will now give the damage variable at the current iteration, which we will again use here for calculating compliance matrix and the constitutive matrix, and the procedure will revolve like this only till we get a converse value of this nodal degree of freedom vector. This is a literature review. So from this literature review, we have characterized the damage models into two categories. One is failure mode independent, other is failure mode dependent. So mainly we are going to focus on this Barbero and Vivo failure mode independent damage model, and this Mattmiller, Lublinar, Taylor failure mode dependent damage model. So in the literature, these are the damage evolution equations that have been proposed by Mattmiller in 1995. So equation 1 is the generalized equation. Now for uniaxial case, the equation 1 reduces to a form like equation 2, but this equation 2 has been, which is only applicable for the uniaxial case, has been used by many people for the 2 or 3 dimensional damage analysis of laminated composite panels, which is not correct because it is only uniaxial equation. It cannot be used for 2 or 3 dimensional analysis. One more research gap is that the damage model parameters of the damage models that are present in the literature have been characterized using only the strength values of the uniaxial stress strain curves, and they have not taken into account the non-linearity present in the uniaxial stress strain curves to characterize the damage model parameters. So these are the three research gaps. The first one is there is no literature available on damage prediction of laminated composite panels using a failure mode dependent damage model, which is characterized using all the points of the uniaxial or shear stress strain curves. Second one is damage prediction capability of thermodynamically consistent and failure mode dependent damage model is not available in the literature. And third one is damage modeling of variable angle to composites using a failure mode dependent and thermodynamically consistent damage model is not available. So that's why we have developed a failure mode dependent damage model, and we have compared with it. We have compared this model with a failure mode independent damage model. So failure mode dependent damage model depends on various modes of damage, that is fiber tension, fiber compression, matrix tension, matrix compression, like that. So we have taken 4 modes of damage as of now. So one, that is fiber tension, fiber compression, matrix tension, and matrix compression. So these are the damage evolution equations. So that have been proposed by Mattmiller for 2D plane stress condition. Now we have developed these equations for generalized plane stress conditions by taking out of plane damage variables also into account. So this is already 2D plane stress stability model is existing in the literature, and this is the developed generalized plane stress model, which is termed as MLT GPS model. So MLT is same as this one, and GPS stands for generalized plane stress condition. Now we will compare this with the failure mode independent damage model, which was proposed by Barbero and Vivo. So now this is the first time that the damage model parameters have been characterized using all uniaxial testing curves. So this is the figure 18 represents the characterization done by Barber and Vigo. So they have only characterized based on this in-plane shear testing curve. They have only taken into account all the points of in-plane shear testing curves. In other direction, they have only taken the strength property. So that's why their curves are not able to match in other directions. Okay, so but in our case we have characterized the damage model parameters by taking into account the non-linearity present in all the directions, by taking all the points that are present in all the directions. So that's why we are able to achieve a greater accuracy in all the uniaxial testing curves as compared to the Barber and Vivo damage model. And this is the first time that we have that somebody has characterized these damage model parameters using all uniaxial testing curves. So this is the finite element procedure that we will follow for damage modeling of this laminated composite panel, which is composite plate which is subjected to uniformly distributed transverse load, and we are going to use this first order shear deformable plate theory. And this will be the flow chart, which will be similar to the numerical solution procedure I explained earlier. So now the results and discussion. So this is the validation of our formulation. So now we are able to see that our formulation matches very well with this associative damage flow rule model, which was uh, modeled in 2005 by Robin et al. But they have used this method 1 for damage modeling, which is not consistent because it was not satisfying the loading criteria. So that's why we have solved damage evolution equation using method 2, and it is predicting a slightly different value of damage variables because it is solved by consistently satisfying the loading criteria. So this figure is through the thickness distribution of this damage variable 2 at the right corner of this plate here, somewhere here. So now one more important observation is that, so this is a so figure 23 represents through the thickness distribution of damage variable 1 and 2 at the center of the laminated composite plate. So now we are able to see that this present model is able to predict different damage variable values in tension and compression of the plate, whereas the Barber and Vivo predicts same damage in tension and compression, which is not consistent with the strength property of the material. So for instance, this present damage model is predicting less damage in fiber tension and more damage in fiber compression, which is consistent with the strength properties because the strength in fiber tension is more and strength in fiber compression is less. So that's why there will be more damage in fiber compression. Similarly, in transverse to fiber direction, we can observe this phenomenon. So in this slide, we have compared the MLT GPS damage model for the two coupling vectors Q1 and Q2. So these coupling vectors take into account the coupling of damage in different directions. For instance, whether the damage in fiber direction is leading to damage in matrix direction or not, or damage in matrix direction is degrading the shear stiffness or not. So figure 24 represents the load versus central deflection curve at the center of laminated composite plate, modeled using coupling vector Q1 and Q2. So coupling vector Q1 is based on yen and Q2 is based on SOSA, and they have the form represented by equation 10. Now in the load versus central deflection curve, we are able to see that the plate without evolving damage, so this dotted black curve is for the plate without evolving damage. So the plate without evolving damage is able to sustain more load for the same central deflection compared to plate with evolving damage, and which is very obvious from the physics point of view as well. Now using coupling vector Q1 and Q2, so this green curve represents coupling vector Q1 and this red curve represents coupling vector Q2. So for the coupling vector Q1, plate is losing its structural stability and load is getting suddenly dropped here, whereas in coupling vector Q2, plate is not losing its structural stability and the micro cracks are coalescing to form a macro crack in coupling vector Q2, whereas in coupling vector Q1 the micro cracks are not coalescing to form a macro crack. Before that only the plate is losing its structural stability. So here we are able to see from the maximum value of damage variable as well, corresponding to Q1 maximum value of damage variable is not 1. Before that only, I mean 1 represents the micro cracks are collision to form a macro crack. So before that only the plate is losing its structural stability, where in case of Q2 the damage variable is reaching to 1. It means there is formation of macro crack, and there is still the structural stability that is left in the plate. We have also plotted the in-plane shear stress and curve at the failure location of the plates. So here we are able to see that since both of the damage variable value are almost closer to 1 and the second one is equal to 1, so that's why the shear stress at that material point is either 0 or closer to 0. It means where it is 0, it means that point has completely lost its stiffness, or that material point has been completely damaged. Whereas here, where it is approximately equal to 0, it means some stiffness is left, but that is very negligible. Before that only the plate is losing its structural stability. So in this slide we are comparing through the thickness variation of damage variable D11 and D22 and the corresponding stresses at the center of laminated composite plate, which is subjected to uniformly distributed transverse load using coupling vector Q1 and Q2. So the coupling vector Q2 is not predicting the damage variable values consistent with the strength properties of the material, because the strength of the fiber reinforced composite material that we have considered, so this material has more strength in fiber tension, but coupling vector Q2 is predicting more damage in fiber tension, so it is not consistent with the strength properties. So that's why we conclude that coupling vector Q1 is consistent with the strength properties of the material. Now these are the new contributions that has been done. Firstly, we have developed a failure mode dependent continuum damage model characterized based on all reactions here, experimental test and curves. Second, we have solved Barber-Vivo associative damage flow rule model by consistently satisfying loading criteria, and where we have compared the developed model with Barber-Vivo model, and it is concluded that the developed model is predicting damage variable values consistent with the strength properties. Third, we have compared the damage prediction capability of the developed model using two different coupling vectors. So these are the conclusions and the future works. In future we are going to develop a thermodynamically consistent damage model and as an extension to the developed damage model, and also we are going to apply the developed model for damage prediction of straight and curvilinear fiber reinforced laminated composite panels, and we are going to investigate damage prediction capability of the developed thermodynamically consistent damage model for its associative and non-associative and local and non-local natures. These are the outcomes of my research. So one book chapter has been accepted in Springer Nature for the publication. I have attended two conferences, one in Portugal and one in IIT Guwahati, and I have submitted a manuscript. And we have submitted a manuscript titled "A Failure Mode Dependent Continuum Damage Model for Thick Laminated Composite Plates in Mechanics of Materials," and it is under review. Okay, so these are the references, and thank you for keeping patience. Thanks a lot.